Hello everyone, welcome to the second part of the presentation. As I mentioned earlier, the first part's all done, it's in the previous part one. The second part, the second video, covers part two and part three of the presentation. So I'm going to talk about in situ stress and the Yilgarn stress measurements, WA sort of mining states of stress, and then a particular example of exactly what might be happening underground where we've got seismicity, and then estimating the sizing and the risk of those seismic events, and finishing up with a bit of risk mitigation information. So in situ stress constraints. In West Australia, here's a picture of the worldwide stress map, which tabulates information from all around the world. You can go online and get their map. So the one on the right is the entire western half of Australia, more or less. Kalgoorlie would be somewhere out here. This is Geraldton, Dongara. In the Yilgarn Craton, we have a lot of information over here, say in Dongara, Geraldton area, the oil and gas drilling fields there. There's a lot of information from breakouts about the orientations and the magnitudes of the stresses. In the middle of the Yilgarn, we don't have a lot of information, very little from mining. There are some small seismic events that have occurred, and those can be inverted to give you an idea of what's going on. And these tend to be reverse faulting states of stress with a generally east-west compression. And this general situation is confirmed where you've got more detailed information from mine-based observations. So the stress in Western Australia, as I mentioned in the earlier part, reverse faulting state of stress in the Andersonian terminology, which means strong horizontal compression. The horizontal stresses are larger than the vertical stress, which is probably the smallest or least compressive stress. Remember, this is in situ stress, which means the current day stress. It's not the tectonic stress or the Archean stress or the stress that's responsible for structures around the mines or around the ore deposits. So just a quick word about how we actually go about calculating the state of stress. We either make measurements or we can do some crude calculations to get us to decide if we're in the sort of correct ballpark. So this is a technique maybe borrowed from the oil and gas industry. If you're drilling a well and you're getting down to depths where your oil and gas reservoir is, this is an example from a basement reservoir, which is a little bit unusual. But typically what we do is we say, okay, here we are. We consider what's going on. We want to know what's the weight of the overburden. So if you're down at 2,000 meters, well, what kind of rock weight is above you? What's the density of the rock and the fluid above you? So basically, you then get a good estimate of the density. So we know the seawater density, which is the little thing there. So if it's offshore, we know the seawater. Then we get a shallow estimate, typically from geotechnical information, and then we've got downhole logging that gives us the information sort of at medium depths. Then if we've got a gap in the logging, we need to get some kind of an estimate. And then in this case, we've got higher densities in the basement rock, which is the deepest part of the well where the basement reservoir is. So then it's just a matter of integrating the equation shown here on the right. The first term is about the density of the water. The acceleration of gravity is g, and z is the depth of the water. And then there's an integral, just meaning we integrate over depth, and the density varies, but again, it's g, the acceleration of gravity, and integrated over depth. Now, if we're in the mining situation, we don't have quite as much information, but in some ways, the geology and the variation in density is a little bit simpler. We're often talking about crystalline terrains that have been uplifted and the top overburden area is gone, so we don't have unconsolidated rocks. And this would be true of much of the Yilgarn. So in this case, we know a lot about the density, even though we don't have quite such continuous information. So ask any of the resource geologists, they'll tell you what the density is, because they need to know and make sense out of the tons and the grade of the ore that's going to be mined. And then they also need to estimate the mass that needs excavation. So that's mining engineers and figuring out, well, how many trucks will it take to get rid of the stuff that's in the pit, and how many trucks will it take to get rid of the stuff that's going to be removed to form our decline. So again, then it's just an integration. We aren't going to have the overburden from the seawater, which is the first term, so I've crossed that out. And so then you might have your estimates of density might look something like the right plot, and then, I'm sorry, the left plot, and then your resulting vertical stress, shown by the dark line as a function of depth. The thing to remember is somewhere around 25 MPa per kilometer is fairly typical. Now, the other thing that is done commonly in the mining industry, which is not so common in oil and gas, is that we do overcore and deformation rate analysis tests. So the CSIRO high cell is one of the common and most popularly used strain gauge. So what happens is you drill a hole, cement this into the rock, and then overcore it, which causes the stresses to relax. Um, the amount of strain that's observed as you overcore it then could be used to back calculate what the stress is, or what the stress was after you've released the stress in the rock immediately surrounding the strain gauges. The deformation rate analysis test is the new kid on the block in a sense. In this case, you sample a core, take it to the laboratory, and then repressurize it until the acoustic emissions start back up. You sort of assume that, well, when that happens, then you're back to the initial or pre-coring state of stress, and then you measure the stresses or calculate them at that point. Neither test is flawless, but they do give fairly good results. It's important to QA and QC these against the estimated overburden, as I mentioned in the previous slide, and see if the vertical stress numbers that it gives you are about right. It's also good to compare this with the Andersonian constraint, and if it departs far from the Andersonian constraint or a simple overburden calculation, then it's important to ask yourself why. But these tests then give measurements of the magnitudes of the stresses and their orientations. So in some cases, they are predicting departures from the Andersonian state of stress that I mentioned earlier. This is an example from Western Australia. So the vertical stress that I showed earlier is in the diagram at the left. That's repeated at the right, and that is a solid black line. The actual observations from the mine site underground are the black, green, and red dots. The black dots are the vertical stress. The green dots are the smaller horizontal stress, and the red dots are the larger horizontal stress. And the lines are an approximate best fit, particularly for the intermediate and maximum horizontal stresses. And you can see there is a fair bit of scatter. It's probably best to think of these values as approximate and good to maybe 10, 20, 30%. So they're quite approximate numbers.